flow from one substance to another and understand whether or not a given reaction will work spontaneously, we can use that electron flow in order to make a circuit. This is going to help us understand how batteries work, because batteries are really voltaic cells. To do this, we separate the two reactions, and then we capture those electrons. Okay, we allow the electrons lost to travel to the other side through a wire. So I want you to look at this picture, and it has all the important parts of a voltaic cell. We're going to do some notations. I've learned how to draw a little bit on Microsoft Word, which is a little bit annoying, but frankly, my handwriting is so bad anyway, then really doesn't make a difference. No. So take a look at this diagram here. Now, we have a strip of zinc that's sitting in a solution of what is essentially zinc 2+, right? Zinc sulfate, sulfate's 2-, so the zinc is 2+. On the other side, we have a copper strip. Sorry, mine's in color, yours isn't. That's the way it goes. The copper sulfate, as you know, is blue. Copper is 2+ here. So this is copper sitting in a bath of copper 2+. We have this thing called a salt bridge. That's kind of new. We'll talk about that a little bit. Don't worry too much about this. This is an ammeter. This is just measuring current. And forget about current flow. I don't really care about that. So I'll start with my first shape here. We'll go freeform. I'll just go like this. Okay, we'll let that, be for physics. Forget about current flow. Electron flow is important, but I bet you could have figured that out if I had just asked you to go to table J. Because table J would tell you that zinc is more likely to be oxidized than copper, which is down here. So the zinc should lose the electrons preferentially to copper. And that's exactly what's happening here. The electrons are flowing from the zinc to the copper. Now, what's actually happening is you've actually separated the oxidation, because here's your loss of electrons. So Leo says, right, Gur. So here's your loss of electrons, which occurs here. And then the electrons are gained on this side. Well, let's think about what happens in that case. I'll do another diagram here. See if I can make this work. Over here, some of the atoms of zinc are going into the zinc solution. And on the other side, ions of copper are glomming onto the copper strip as the reduction occurs. Okay? So you have atoms of zinc becoming ions of zinc, and you have ions of copper becoming atoms of copper. So if you were to write the half reaction, this is what you're going to have to do in a second, the half reaction going on this side, it will represent the oxidation of zinc to zinc 2+, and then this will be the reduction of copper 2+ to copper solid. So we're going to label these things. We have electrodes and we have wire, salt bridge, and a half cell. The wire is wires right here. These right here are half cells. That's a half cell. And you should label it as such. I know I'm having fun with my freeform shapes here, but you've got to label a little bit better than I am. And that is a half cell. So you have two half cells making a whole voltaic cell, that's what it's called. And the electrons are flowing along the wire. So if you were to stop this wire, you could actually capture that electricity, like, and power a toy. Like one of those dogs that go beep, 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 and flip over, and you remember those, okay? They're all good. In any case, at one of these half cells, oxidation is occurring, that's the zinc, and at one of these half cells, reduction is occurring. So which way the electrons flow? They flow from the zinc to the copper. And specifically, they flow from the zinc strip to the copper strip. These strips are called electrodes. Oh, sorry, which of these elements is going to be oxidized? We kind of already said it, but we can write it down here if you like. Oops. Now, the salt bridge is a little bit strange. What is going on with the salt bridge? Well, In order to think about that, I need you to think about what happens to the charge. If electrons are being lost here from the zinc side, what kind of charge is going to be developing as electrons are being lost? If you're thinking positive, then that's the right move. And on this side, electrons are being gained, so you're going to get a negative charge building up here. Now I have to ask, would you expect that if electrons are flowing towards the copper, and this whole cell is becoming slightly negative, that electrons, which are negatively charged, would they keep going towards the copper? Would negative things keep going towards negative things? Of course they wouldn't. And so that's what the salt bridge is for. The salt bridge is going to help balance out the charge that would have otherwise built up in the cells. All right, so what do you need to know? That's the explanation. What do you need to know? First of all, the salt bridge is right here, and it must have uninvolved ions. For instance, in this case, we've got copper and zinc sulfate, so you could use potassium nitrate, aqueous, so you dissolve it. Anything else, sodium chloride, that would be fine. We're going to use that also. The point is you need uninvolved ions here in the salt bridge. So you actually soak like a piece of filter paper in like you have a side beaker that has potassium nitrate in it, and you soak it, and then you put it in the beaker one side, and you have to touch each side. Now the reason we do this is because now think about it. You've had a negative charge building up in this half cell. You want the electrons to keep flowing because, my goodness, you really like your dog toy and you want it to keep working. So you need electrons to keep flowing through the wire. So what happens is, as a negative charge builds up, coming out of the salt bridge are going to be some positive charges. Oh, that's annoying. So coming out will be positive charges to balance out the negative charge. And on the other side, and I'm going to have you draw it so I don't take forever, you're going to have negative ions. In other words, the nitrate would come out on this side to offset the positive charge that would be building up here on the oxidation side. And so this salt bridge helps to complete the circuit. Now, the one thing that you cannot ever tell me is that electrons are flowing through the salt bridge. Electrons don't travel through paper. They travel through the wire. So that's an important piece. So what is the salt bridge? It is, here, I'll put it in bold for you. It is a piece of filter paper. It can be other things, but filter paper is the most common thing. Soaked in a solution of uninvolved ions, which helps complete the circuit. Or helps to allow the flow of electrons through the wire. Important, not through you can't flow through the salt bridge. Or promotes the flow of ions to balance the charge. The charge, yes, the charge. And this is important, and I want you to write it in all caps too. Electrons do not move through paper. Okay, amazing concept, but you'll be surprised at how many people make this mistake, and don't let it be you. Okay, don't be you. Oh, what's the function? I already answered that question. What's the function of the salt bridge? All right, you've determined where reduction and oxidation occur. These each occur at electrodes. The electrodes have different names. Oxidation always occurs at an electrode called the anode. Reduction always occurs at a cathode. Label the anode and the cathode. The anode and the cathode are the strips of metal. Label them. Next mnemonic. Anox, red cat. Anode oxidation, reduction at the cathode. You need to meow at me when you come back to class. See ya.